And I'm Anders.
And I'm Carl-Johan, and we have Ava. She will be here right in a moment.
Join her.
Yeah,
Soon. We welcome you here to Gymnasium when we have worked fairly hard and enthusiastic on this case, and we hope you like it. You gave us this case. We were supposed to find creative ways to find ways to drop these pills down, wrapped in some chemistry, down a 12-meter deep pipe. The case had several limitations. Our solution should be fairly simple, and we couldn't use hydrogen oxide, and the pills must be dropped from 80 to 180 centimeters above the bottom, and so on and so on. We also had some limitations in the way of perfecting a product. We could of course not simulate a 12-meter deep pipe. We had these, but nor could we use the optimal materials such as aluminum or plastic or whatever. And you have the time and resources to make a valid and perfect a product. So we saw our purpose in this case you gave us more as to find funny and great ideas that could inspire you into a creative process and maybe even towards a product. Therefore, our presentation and ideas might seem a bit unpolished. But that being said, let's go in step.
So catalysis, we have seen this 3 times already. We'll see it 4 more times. So I'm just gonna skim over it quickly. So catalysis is just increasing the rate of a reaction rate of a reaction by adding catalyst. And I thought that the fact that you managed to get a surface area of 100 square meters in these little pellets is quite cool. And of course, is I think one of the main points attributes as to why you can achieve such a high reaction rate. Right to modern society, without catalyst, the demand for the product of the reaction is so high that we need this reaction to be quick. So you have seen this once before. So just without a catalyst, there's a high barrier to entry. You need a lot of energy for the reaction to start, and with a catalyst, there's a lot less energy required. Temperature, when you heat up when the reaction is hot, the molecules move a lot quicker. They hit each other a lot more often, but they also hit each other with more energy, so the energy barrier is easily overcome.
Yes, so let's, as an example, take a look at this reaction where hydrogen peroxide is converted into dioxygen and water. This reaction demands a certain activation energy for it to go off, and this activation energy is higher than if we add a catalyst, in this case iodide. Now the reaction proceeds in 2 steps. In the first step, hydrogen peroxide reacts with the catalyst iodide and makes hypoiodide and water. And after that, in the second step, hydrogen peroxide reacts with the hypoiodide and produces iodide and water and dioxygen. And in this way, we end up with the same product, but the activation energy for the 2 catalyzed reactions is much lower than the uncatalyzed reaction, and therefore more molecules possess the activation energy, and the speed becomes much higher. And the reason why this is so smart is partly that we reduce the activation energy, and also that the catalyst gets reproduced, so we don't even have to add very much of it for this to work. So yes, so we began the process of creating new ideas for a solution to the case, and our first idea was to create a slide that allowed the catalyst to roll the entire way down to the bottom of the pipe. And the slide would have the shape of a helipad, to fit into the reactor pipe. And if the slope of the helicoid descends at least 24 centimeters per rotation, the helicoid would easily operate around the two metal bars that keep the inner pipe in place. Yeah, as you can see. But the catalyst cannot fall from a height of more than 3 meters. And if they do so, they will break because they hit the ground with a too great velocity. And due to the steep slope of the helicoid, the catalysts that slide down will hit the ground with a too high velocity, excluding friction. So if this is to work, the helicoid slide must be made so that it creates a lot of friction when the catalysts slide down. Another thing that is important to notice is that you cannot hold a 12-meter high helicoid vertical on the surface of the ground while screwing it into the pipes, and therefore the helicoid must be made in smaller pieces that can be put together when one by one when they're screwed into the pipe, and that can be a little hard to handle. But if you could do so, you could also make the different pieces of helicoid magazines with catalysts, so they would not need to be put in manually from the top of the helicoid, but could fall from only 1 meter above the ground or the bottom. Only the helicoid occupies a lot of space inside the pipe, and it would have to drop catalysts from more than 3 meters of the helicoid to fill only 1 meter of the pipe.
Yeah, so this is a new idea. All the past have been most from the same group. So we started off by building upon this magazine idea that, we made a semicircle shaped magazines. So they're very basic. They load like magazines for a gun, so you can have them loaded elsewhere and then just use them when needed be. They're very efficient. They don't have intricate shapes. They're quite easy to manage. They're simple to operate. There's no fancy whatever. It's just opening and closing the bottom of the magazine. And there's two ways of really doing this we thought of. The first one is a piggyback. So you have the first magazine you load in has a port that can open and close, and the rest are just on top, filling the first magazine with catalysts. That can be a little tricky to manage the flow, but our second idea was to unload them separately. So you just load one magazine in, unload it, pull it out, and then add another magazine in. And some of the cons, material requirements, port opening and closing, can be a little difficult, especially if you choose the piggyback method, because you might have quite a high pressure on top, and you might encounter problems with pellets being stuck in the port and so on. Managing catalyst flow, connecting with the magazines, that would have to be some sort of lateral connection. You can't really twist them inside the pipes to lock them together. They're easy to store. They can be loaded elsewhere, so they can be done at HQs and maybe done by machines. You don't have to manually load every single one of them. Fixes the slide speed issue where you have to think about friction and speed. And you can double them up, so you can just, if you choose the separate loading mechanism, you can just run them up and down each side pretty efficiently, and they aren't really difficult to use at all.
Like beads on a string was one of the last ideas we came up with. We were working exclusively and focused on the helicoid project and the magazines. And we were so annoyed that the helicoid required so much space and material in the inner pipe. So we wanted to find a solution that required the least possible resources. And that was when we started to work with strings. I showed there. So we came up with this idea. It's super simple. We place the catalyst pills like beads on the string, and then we have these needles that work as a trigger and also uphold the pills. And I think we should just show how. So, as the trigger reaction is super simple, we we can pull and pretty much like now this was just you can see there's probably a fail rate, but this is the general idea. So by shortening the length of the lowest needle with an additional string, we can make a fall order that makes the one at the bottom fall first. So this has a lot of potential. We can stack 12 meters of catalyst on one string and then place them really close to each other down the whole pipe. This way we have a potential of stacking really quickly and efficiently. And to pros and cons. So our first con is it's clumsy, probably. It can tangle when handling with the strings, and so you would have to be careful. Even you can probably work out a solution to that, but still it would need careful handling by workers. And also it would require pre-packing, which also could be expensive. It's manually it's really hard to set up these catalysts on the strings, so it would require some pre-packing. And as pros, it is very material efficient, like extremely, and that also means it's lightweighted, and we can quickly pack the pipes with the catalysts. And it's super simple. The trigger mechanism and the way of packing. Maybe too simple, as you explained. It should look expensive, but I actually think it does a bit. I think it's a great idea. Yeah, we are proud of
And the whole idea was, we thought, hey, no matter what we do, we got a mechanism that we need to pull out from the pipe manually, and then say, how can we make something that we don't have to pull out the pipe again? And we thought of something that would vanish entirely by itself, and that would dry ice, which is solid carbon dioxide that has been made solid because of pressure and cold. So the point was that we are going to fill a pipe with the dry ice, and then we're going to pour out the catalysts on top of it. And slowly, as the dry ice sublimes, we can pour in more catalyst, and they'll just come down by themselves. They won't fall, and it's very important that they don't break, and they won't break this way, so we don't have to make sure they're not going down. And the other very first thing you notice is you don't need to pull the mechanism out of it. But on the other hand, it's really, really hard handling the solid carbon dioxide, especially because it's really cold. It's minus 78 degrees Celsius, which means you can't touch it. You have to wear protective gloves. Maybe the catalysts can't take it. And like it. And the other one is that it's unhealthy. You can't consume it. And when sublimed, carbon dioxide is toxic to breathe. Also, when you put all the dry ice into the catalyst, it's going to take quite a long time for it to sublime. It does quickly when it's warmer, but of course it has to be needed. It has to be watched the entire process because you have to pour in more catalysts as you go. But on the other hand, this means that one person can look after several pipes, maybe even the whole reactor at one time. Makes it quite simpler. So the other catch about the carbon dioxide is that it's heavier than the air that we breathe. So it's going to stay down in the pipe. Or some of it is going to come out because when sublimes, takes up more room and comes out of the pipe and you can't breathe it, of course. But the other thing is that some of the gas is going to stay in there because it's heavier than the air. And the very last one is that all of you has probably tried to put dry ice into water, and when it does, it creates this heavy white fog. So yeah, that's not good. So no rain, please. So make a little bit of summary. So we made 4 models: the helicoid, the magazines, the strings, and the one with the dry ice. But as we were testing those, there was a lot of issues. The first one is we weren't able to build the helicoid ourselves because the helicoid is a minimum surface, and all we had was cardboard, which is also what our magazines were built of when we tested them. That's not, well, it's not the best thing in the world, I'd say, especially when testing it. The strings, if you didn't see, we had a little bit of fail on them. That's because these little things here are sewing needles. Yeah, that could be made more effective too. It's a nylon string that we just burnt and then put the needles through. And the last thing is that there's no way we can handle enough dry ice to fill up those pipes, who probably wouldn't survive if we did. So most of this is just ideas that we've been trying to calculate a bit on, and then, well, we think they're quite good. And we're very proud to present them to you. And thank you for this opportunity to work with this.